I'm going to talk to you today a bit about just some part of my own research, and then a bit about the work Jeremy and I recently did. And then, after that, I'll give it over to Jeremy, who's going to provide you a bit more context and maybe look a bit more in the future for future directions. So just to give you a bit of broader context here, over the course of my PhD, I've mainly focused on kind of problems that broadly relate to transfer learning. So basically, I've tried to work in settings where there's limited amounts of label data and trying to use data from different sources to improve performance on downstream tasks. And in that, I've mainly initially worked on kind of different scenarios for domain adaptation, so leveraging data from different domains to improve performance. I've also worked on using data from different tasks, mainly by trying to develop new methods for doing multitask learning that go beyond simply hard parameter sharing. And then lately, I've also done a bit of work on learning across languages, mainly by focusing on approaches that induce a joint cross-lingual word-embedding space, and essentially trying to understand better the current limitations of these methods and proposing methods that in particular are most suited for the low-resource scenario. But today, just to keep it a bit brief, I'm mainly going to focus on the first aspect here, mainly because I think it's also part of that kind of addresses something that lies at the heart of machine learning, which is that in general for machine learning, we really assume that the data we're dealing with is independent and identically distributed. But as we try to apply our models to kind of a more diversity of tasks or to real world applications, we realize that they often deteriorate in performance. And so one thing that I want to kind of emphasize throughout the talk is that if we just measure the performance of our models on data of the same distribution, we never can actually be really sure how well they truly generalize. And one kind of example I found interesting in kind of in this direction was from a recent paper by Ben Recht et al., where they essentially showed that even if we create a data set or even if we create a new test set that comes from the same distribution for Cypher10, which is a widely studied image classification data set, even on this data set from supposedly the same distribution, the models fare worse. Because they've overfit, or because we've been overfitting for state-of-the-art models on data of exactly the same distribution or the same test set. And kind of one quote that is really much in line with the message I'm trying to convey here in this talk is from Percy Liang, a professor at Stanford, which he uttered at the recent generalization workshop at NACL, and where he basically tried to encourage the community to be a bit more kind of braver in their evaluations by essentially posing as a challenge to evaluate our models on more diverse tasks and on different or out of distribution data, just to get a better understanding of really how well our models truly generalize. And kind of with this in mind, I'm mainly going to talk about two settings kind of in this line of work. Firstly, I'm going to talk about how we can leverage unlabeled data for learning across domains. And in this regard, I'm mainly going to focus on how we can combine kind of classic semi-supervised learning algorithms with current neural network approaches. And the setting I'm going to be looking at here is that we have one source task and one source domain. So here for a classic data set, we would have for sentiment analysis a product review domain consisting of electronic reviews, and we would try to train a model that can adapt or generalize to a new target, to a different target domain like kitchen reviews, but again of the same task in this case. And for this setting, just to give you a bit more background, a lot of state-of-the-art domain adaptation approaches for this kind of setting really kind of try to leverage or rely on task-specific features. So there have been a lot of approaches that try, for sentiment analysis, for instance, that rely on sentiment-specific words, or for part of speech tagging that rely on distributional features which are specific to that particular task. In addition, a lot of the approaches also evaluate either just on one particular task and on one particular data set or a proprietary data set of that task, which makes it difficult to replicate or compare different approaches across different tasks. And finally, what we notice as well is that a lot of these approaches also compare just against, maybe somewhat weak baselines, in that they mostly compare just against like a source-only baseline or ablations of their own model, in contrast to, just a broader variety of stronger baselines. And in particular, we found that none of these like recent neural-based approaches really compare against kind of any more classic approaches, and in particular, none of them compare against any of these approaches from kind of the huge body of semi-supervised learning literature. And in this talk, we mainly, or in this piece here, I'm mainly trying to view here essentially kind of classic semi-supervised learning through like a neural network type lens, in order to answer essentially if these classic methods, how well they can compare to our recent advances, if there's a way to combine the best of both worlds in some way, so to get benefits from both our neural models as well as maybe some intuitions or some lessons to learn from these classic approaches. And then finally, if how well these classic approaches actually work on out-of-distribution data as well. And so the kind of approaches I'm going to be looking at mainly here are so-called bootstrapping approaches, mainly because they try to use the predictions of the own model essentially to lift the model with their own bootstraps. The kind of approaches I'm going to be looking at here are three essentially. So I'm going to be looking at kind of the most prototypical, the most simple method to use models on prediction for semi-supervised learning, which is called self-training. Another approach that maybe most of you have probably heard of is co-training. I'm not going to be talking about that here though, because co-training kind of intrinsically relies on having mutually independent views of the training data, which in kind of some settings is like not that easy to get. So it's a bit more of a restrictive use in many scenarios. And the other two approaches I'm going to be looking at are try-training, which uses three models for learning, and then try-training with disagreement, which is a kind of simple extension of try-training. And so coming to self-training here, if you're not familiar with that method, it's basically kind of the simplest method you can think of to use models on prediction for semi-supervised learning. And it works essentially by kind of two main steps. You first train your model on all of the labeled data, and then after having trained the model, you simply apply it to the unlabeled data and use and take the most confident predictions of the model essentially at face value. So the most confident predictions of your model from over some threshold, you would add kind of as face value as gold examples to your label data and kind of repeat that process by continuing to produce predictions on the unlabeled data. And as you can probably see here, by kind of continuing this cycle, the model really has no way to actually correct mistakes it made early in training. So kind of the core limitation of self-training really is that during training, its errors will actually get amplified. And in some cases, this will result in actually poorer performance than if you just trained a model solely on your source domain, or it might even lead to just the training of the model totally diverging. And because of this kind of inherent limitation, self-training mostly had limited success in NLP. So there's been some early success stories in parsing, mainly in settings where you have small amounts of label data. But then kind of a bit more recently in other tasks, there was more limited success. And one kind of more interesting recent example from computer vision, where they use self-training essentially on kind of an ensemble of different transformations of an input example, on using that to learn from web scale unlabeled images. And they actually observed improvements just using this very simple method, actually, with not really any other modifications. And for using self-training with neural networks, there's a couple of considerations we would like to make. Mainly, as probably most of you know, the output probabilities of neural networks are really kind of a poor predictor of the actual confidence in the example. So instead of using a threshold, we actually found it more useful to just use something that is called throttling, which is essentially that you just try to use the top n most highest confident examples for training. And then secondly, most classic approaches that have been used with self-training, like support vector machines, for instance, are trained kind of in a batch mode. So you would train it on the labeled data and then apply it on the unlabeled data. whereas neural networks, you are basically trained online in most cases. So here you want to basically decide at what time or what point in training do you want to mix in your unlabeled examples. And here we found it to work best to first train the model until convergence on the labeled data, so you have some already somewhat reliable measure of confidence, and then continue the self-training loop from then on. So proceeding to the next method here, which I think is one of the more kind of interesting ones for semi-supervised learning, which is called Pretraining. And the name comes from the fact that the method essentially requires 3 independent models. And the key feature or the key characteristic of Pretraining is that you want to have these 3 models to be as diverse as possible. So you want them to rely on different features or different representations for learning, so that they can actually help each other and kind of collaborate in improving each other's predictions. And kind of the most popular or the typical way you would try to enforce this diversity is by having kind of the models with the same architecture, but training them simply on bootstrap samples of the training data, so that each of them would kind of see different labeled examples during training. And then in the Pretraining loop, you would then take each of the 2 models in turn, and basically, given an unlabeled example, ask both of them for their predictions. And once 2 models agree on the predictions, you would then add that prediction as a kind of as a gold example to the 3rd model. Essentially using kind of the agreement of 2 models as a measure of confidence in that unlabeled example. And then for getting the final prediction, you would typically just use a majority voting over these examples, over the 3 models here. So just query them to get the final prediction. And similar to that, Pretraining with disagreement does essentially the same thing with one kind of key modification. So instead of using all examples where 2 models agree, you also will query the 3rd model and only add examples to the 3rd model if the 3rd model disagrees with that with the first 2 models' predictions. And that kind of mainly comes from the intuition that with Pretraining with disagreement, you don't want to add examples that are kind of redundant for training. So you don't want examples that the model already can do well on anyway. So you rather want examples where you have a good chance that the 3rd model can improve their predictions on those. And for Pretraining with disagreement, the main downside of those is, as you can see, that you require essentially 3 independent models to train. And if you use bootstrap samples as well, you require that you have that you also store kind of 3 separate variants of the label data in memory, basically. Which is, it can be expensive, particularly if you have a lot of label data, and if your unlabeled data is quite a lot as well. And for, sorry.
How important is it in the Pretraining that the models are trained using independent features rather than just having 3 models? Like if I take a neural network and train it 3 times, does this work or not?
So if you train it 3, I mean, ideally you want to have some way of having some sort of diversity with the models. I mean, so here Pretraining is also, you can see it because of the majority voting. It's also a bit similar to like ensembling. So if you would just train a model 3 times, you ensemble it, you maybe get some performance improvement. But in this case, you can leverage the unlabeled data as well. But similarly, like rather than doing bootstrap sampling, you could also have like different models that have different architectures or different hyperparameters, for instance, which would then maybe, or different like number of layers, which would then hopefully also induce kind of some diversity in the models. Yeah. So there's different ways. Like classically, you could also have just different models of different types, like a linear classifier, a support vector machine, a decision tree or so, and and use those for Pretraining. Yeah.
But then also you have so much variability in the protocol, right? And any conclusion that you can reach may not be statistically insignificant.
For
Let's say if you find out that for the first 2 models you use a combination of SVM and maybe tree-based model, right?
Mm-hmm.
But the performance gain that you achieve with that specific configuration is not statistically significant because it just happens to be lucky because you have so much variability in the setup.
okay. I'm not sure if you have more variability than just like using random initializations. In neural networks, with random initialization, you get also more variability. Yeah, I mean, sure, in those cases, you might want to have like multiple runs, but in general, in our experience, we haven't really observed there to be like too much variance in the results. So it still somewhat converges, like you don't really have like a drastic difference in the kind of result you converge to. Yeah.
So in this case, what do you take? Like, do you take the disagreed Y labels as the goal, or do you take the agreement? Because either of those could be correct, or both of those could be wrong.
Yeah. So here, so in this case, you take So you take like the agreement of the two and assume that's like the correct one. Yeah.
Yeah. So it's like a very strong assumption because you don't know if that is correct.
Yeah. I mean, like here, so kind of similarly, like in self-training, you have the assumption that like whatever is predicted with high confidence is correct, which is probably in most cases not that reliable. And here you maybe have like also still a somewhat strong assumption, but which is maybe more reliable in that if two models agree, that you're going to be more correct like more of the time. But yeah, like it's still just one assumption as well that hopefully introduces some bias that might be helpful in learning, but still it's not going to be correct like 100% of the time.
So I remember back when co-training was originally introduced, there was a little bit of theory, and the paper was like there was like half the paper was here's this
Right.
idea, here are experiments, and then half the paper was this crazy theory that didn't seem to align perfectly well with the realistic assumptions that were made in the experiments. But it worked, and so people got excited and used it. But I'm wondering, is there any theory at all for this one, or try training with twist?
Yeah, that's a good question. I've tried to like in the I've been looking for that as well, but I haven't seen much theory actually at all, or like a kind of I'm not really aware of any like guarantee or bounding on the error you can get with that. I think would be really cool to have a bit more theoretical understanding, but I'm not really aware of any. Yeah. Cool, all right. And so similarly with Pretraining here, we have a couple of considerations we want to make when applying that to neural networks. Essentially, we have a very large pool of unlabeled examples. We don't or might not want to predict on all of these examples at the same time in every iteration. So instead, we found it useful to just sample a number of unlabeled examples at every iteration, essentially. And we also found it useful to just, instead of just sampling a constant or fixed number of examples, kind of to use a schedule, so that in the beginning, when the models are still a bit more uncertain, to sample like a small number of unlabeled examples and to gradually increase that number over the course of training. And similarly, so similar to self-training, we can also try to use some measure of confidence to kind of improve the reliability of these models. And so similarly, we could use like a confidence threshold here and only select examples that have a probability that is higher than the threshold. But we didn't actually observe that to be useful for these classic approaches. But in the method I'm going to talk about now, that was actually, we saw quite a bit of improvement using that. And now, getting to kind of building or trying to mitigate this, the main deficiency of Pretraining, which is that it's very expensive in just the time and the space it takes to train that method. We try to come up with a new method that kind of uses some elements of neural networks to ameliorate that. And the method that we came up with here is, we call that multitask Pretraining. And so essentially, instead of training 3 independent models, we train one model. We essentially share the parameters of those models so that we have essentially one model which has 3 different objective functions. And so you can think of that so it's not maybe not kind of classic multitask learning in that we have in this case the 3 objective functions actually have the same objective, so they predict the same thing. But the 3 objective functions are just trained with different examples, so that over the course of training they would kind of induce or rely on different representations for their predictions. And so the way we train this method is essentially identical to classic Pretraining in that we, for each unlabeled example, we query two of the objective functions and add then that example to the data set of the third objective function if the two objective functions agree. And the main the main consideration here is that we want two of the objective functions essentially to, similar to try-training, we want them to be as diverse as possible, because if we just train this model out of the box with no no constraint or no way to enforce diversity, all of the objective functions would essentially converge to have the same parameters. So we'd essentially just be doing self-training. So so if all of the objective functions have the same parameters, we would get the same prediction in every case. So the model would just learn from itself. Whereas in this case, we share all of the parameters except for the outer softmax layers, and we want the softmax layers to rely on different features for the predictions. And in addition, because we enforce this, I'm going to show how this diversity looks like in a second. And in addition, because we enforce that between two objective layers, we also, as I mentioned before, we also would like our model to do well, especially on out-of-distribution data. So in order to make it easier for the model to kind of really capture the features that are inherent in the target domain, we only train the third objective function on kind of the pseudo-label data that has been created through try-training. So to make it easier for that objective function to really only focus on features of that particular target domain. And
sorry, I'm a little confused. So the three objective functions, they're not three different tasks. They're all the same classification.
Exactly,
task,
yeah.
But they're differentiated because you're assigning different data instances to them.
Yes, yeah.
That's it. They're all the same loss function.
Exactly, they're all the same loss functions, but have like separate parameters and basically get updated with different examples. Yeah.
But they have their own parameters.
They have their own parameters. Okay. Yeah. So maybe I'll just show that in detail, and if that's still unclear, then you can ask again. So just to show how that looks like for part of speech tagging task. So our model is essentially just a classic part of speech tagging model, which is a BILSTM that uses both character-based word representations as well as just a word embedding as input, and that goes for both forward and backward over the text. And at every time step, we then have three objective functions where two are trained on both the labeled and the pseudo-labeled unlabeled examples. And the third objective function is only trained on the pseudo-labeled examples. And then between the first two objective functions, we enforce diversity by basically encouraging the objective functions to be, or the parameters in the objective functions to be orthogonal to each other. By inducing basically, by just inducing like the squared Frobenius norm on the product of the matrices, and that has been shown to in kind of the domain adaptation literature to help essentially and to encourage these parameters to focus on different features because of this restriction that they have to be orthogonal. So they have to rely on different representations for making the final prediction. And then,
Sorry, are these parameters only on the last layer?
Yeah, exactly. Those are only on the last layer. So really only just the linear, the matrix we use to project it to the number of classes in the softmax. We tried that also to have like another linear layer in between, and then the softmax, but that didn't really make a difference for us. Yeah.
Is this a pairwise constraint between all pairs of the?
So this is only a constraint between the first two objective function 1, objective function 2. Yeah.
Because the third one's on the second page.
Yeah, exactly. The third one, like we initially tried, or like ideally we would have liked a pairwise constraint, but because of the orthogonality, if we enforce like pairwise orthogonality, then two of them are going to be the same, right? So because of that, we're only going to do it on the two ones, and by training the third one on pseudo-label examples, we also try to enforce orthogonality in that way. Yeah.
So if you had like redundant or highly correlated features in your include representations, though, this wouldn't necessarily force them to be sort of that diverse, right?
Right. Yeah. So by doing that, we essentially kind of hope or kind of assume that the model also learns to separate in some way the features in the BILSTM essentially. That they can that then later the objective functions can kind of still rely on different features. Yeah, that's a good point. And then finally for training the model, we essentially have just a class a standard like cross entropy loss, and we simply add this orthogonality constraint as a penalization term to the loss. And for evaluating, we evaluate this model on essentially two different tasks, to really understand what are its weaknesses and its strengths. So we compared both on a multi-domain sentiment analysis dataset, as well as on a dataset with multiple domains for part-of speech tagging. The sentiment dataset has like different product review domains, and the part of speech tagging dataset has different kind of web corpora domains like emails, messages, forum data, or blogs. And then just talking briefly here about the results. So comparing that on sentiment analysis against kind of state-of-the-art methods, as well as a source-only baseline, we find that surprisingly for us, self-training actually gave some boost over just using the source-only baseline. If we then use try-training as well, try-training actually gave a considerable boost, and in particular was able to outperform like recent more state-of-the-art domain adaptation approaches on this task. Using try-training with disagreement actually didn't give much of a boost on this dataset. And then finally, our method kind of very slightly edged out try-training on this dataset while having a higher variance, but also being about 5 to 6 times faster doing training than try-training. And yeah, so just looking at these examples, we would see that our method is actually quite competitive. But to get a bit of a broader or more comprehensive picture, we also evaluate on part of speech tagging. And on part of speech tagging, the picture is slightly different. So on part of speech tagging, comparing that against the source-only baseline, we find that actually self-training actually achieves worse performance. If we use try-training, that actually gives another boost in performance, but in the setting where we only use 10% of labeled examples, there try-training with disagreement actually performs better in this kind of setting of using fewer number of labeled examples. And then, unfortunately, our method here really only slightly is better than the source-only baseline, so it doesn't so that doesn't seem to do that well on this kind of setting in part of speech tagging where the domains are very similar. So this, this training on the pseudo-label data might not be that helpful in this case. And then finally, on the full data setting, so the setting where we use all label examples for part of speech tagging and comparing that to kind of some existing taggers and averaging the results over all 5 target domains. Again, try-training really does quite well. Try-training with disagreement works is kind of less useful in this full data setting. And then finally, our method is only kind of competitive with the try-training with disagreement method. And in order to kind of gain a better understanding on what kind of tokens or what kind of word tag combinations this approach really fares, or these kind of approaches fare well or do worse, we did a bit more analyses. In particular, we looked at the performance on out-of-vocabulary tokens. And here, just for these domains in this dataset generally have a comparatively very high ratio of out-of-vocabulary tokens, so are quite challenging in that respect. So we have ratios of about 6 to 11% compared to about 2% for the Wall Street Journal. And in those cases, if we compare classic try-training against the source-only baseline, the classic try-training actually works quite well on out-of-vocabulary tokens, while our method here actually does worse than the source-only baseline on the out-of-vocabulary tokens. So there's still some, even though we use character-based word embeddings, there's still some performance differential to overcome. And then secondly, looking at tokens kind of ordered by their frequencies, we also find that try-training works quite well on these low-frequency tokens compared to here this kind of the improvement against the source-only baseline on the y-axis. And then finally, looking at perhaps the most challenging setting, which is word tag combinations that haven't been seen during trained data, which are also quite common in these datasets. And in those cases, if we compare try-training, multitask try-training against the source-only baseline, we actually find that none of these semi-supervised learning methods using neural networks are actually able to really outperform the source-only baseline. So in this setting, where we really try to generalize to word tag combinations that we haven't seen before, just simply using these kind of semi-supervised learning methods, we're actually not able to do a very good job using those. But then if we use maybe kind of a more classic approach or like a non-neural approach that just uses distributional features like the floors tagger here, that actually performs a lot better than using these semi-supervised approaches. So there's really, so if we just look kind of on the macro picture, just on performance metrics, we're able to get like competitive performance, but really using looking at these more challenging settings, there's still a lot of work to be done. And then, yeah.
You say a few words on the source domain. What is it?
So the sort, so in all the settings, the source domain is the Wall Street Journal, and we try to, we have labeled data from the Wall Street Journal, and we have unlabeled data in all of these target domains. Cool. All right, and so just to give here, the takeaways from this part of the talk is mainly that classic try-training actually works surprisingly well and actually outperforms state-of-the-art methods on sentiment analysis. And we propose a method that try to address like the main drawback of try-training, and that worked better than try-training, or slightly better than try-training on sentiment, but not on passive speech tagging. And finally, with this talk, really want to emphasize again how important it is to really compare our models against strong baselines, really to make sure that we are seeing significant improvements, and also the importance of evaluating across multiple tasks and across multiple domains, really to get a more comprehensive picture of the generalization ability. And now, finally, I'm just going to give a brief.
Sorry, before you go on, I'm thinking about applying try-training in the part-of-speech tagging case, and this is like a minute little technical detail, but you showed in your examples, you kind of showed how it worked for binary classification, where they can vote. But I'm kind of guessing when you do part-of-speech tagging, you're classifying each word.
Right.
You're not doing structured prediction. You're just thinking, what's the tag for this word? What if they all say different things? It doesn't matter, I guess, because you don't need a majority vote in your method. But in try-training, you do. At the end, you just vote, right?
Yeah, like in those cases, for for non-binary prediction, we just basically just average the probabilities and then just took the highest one. Yeah. So there might be potentially a better method to do that. Yeah.
Did you try with more than 2 or 3 models?
So we didn't try in this case, but there's actually been some maybe like a decade ago, some extensions of try training to like more models. Basically, not sure I think like 3 is like the sweet spot or so. I'm not sure. I don't remember any study which shows, I think, there's some diminishing return if you add more models. But potentially you could treat that as like similarly to assembling. If you add more models, you might get some additional improvement, basically.
So you mentioned the importance of comparing classics to neural methods, but I guess I'm not sure what do you mean by neural methods in this context?
So neural methods more the like kind of state-of-the-art domain adaptation methods, basically.
Which were they represented in the results?
So those were the ones we compared to again in sentiment analysis, for instance. Yeah, those were like kind of different methods that use like domain adversarial losses, which are just main like neural network-based methods.
And what's your conclusion based on the set of experiments that you have, or if any, because the results are kind of mixed?
Generally, really that these kind of that I think it's good or important to look for at classic methods, and these can really make for good baselines. Just to compare to that, we can make sure that the new methods we propose actually improve upon those, or that we just have kind of using those as a strong baseline to compare to. Yeah.
I'm not clear on the space and time complexity that you mentioned. Can you elaborate?
So that was mainly the space complexity in terms of using bootstrap sampling, that we need to store more like 3 variants of the training set, basically, whereas in our case we can just train, because of using this orthogonality constraint, we don't need the bootstrap sampling anymore, so we can just train on the same label data set for all models. And then the time, essentially, that for the other one, if you don't parallelize the train, like you could potentially like parallelize try-training, like the initial training of the methods, but if you don't do that, you need to train like 3 separate models. And in contrast, our method, because we're using multitask learning, it's faster to train like one set of parameters than three sets independently. So that was about like 5 times faster than doing that.
The workflow looks more like a standard supervised learning setup.
Exactly, yeah.
So traditionally with ensemble and tagging kind of models, high bias models like decision trees tend to work well. Did you notice anything similar, that the individual submodels in try training doesn't matter if they have high bias or high variance, or like more parameters versus fewer parameters within the model?
Yeah, that's a very good point. I mean, yeah, so for assembling or like boosting as well, so usually it's enough if you have like weak classifiers. Yeah, we didn't go too much down that route, so we didn't really try to. Yeah, we didn't look too much into what is like the minimum viable classifier you might want to use or so. But yeah, that would be interesting to analyze.
So another classic method for domain adaptation is how domains work. And this is on frustratingly easy
Domain adaptation.
And there is some variation of it in the neural case. Do you have any results on this, and how does it compare to the methods that you?
I mean, I'm aware of that, and there's been. I think for that method, there's been like some very cool, good extensions to that, or using kind of adapting that to the neural setting. So I think there's been some good progress in that direction. I mean, here, yeah, we didn't compare against that that had been evaluated before on the sentiment analysis data set, so we could potentially kind of compare against that. But here we focus mainly on these kind of semi-supervised learning methods, because they hadn't really been like considered in that kind of direction. Yeah.
Do you want to go an extra 5 minutes?
Yeah, exactly. So I think I'll just I'll just do like 5 minutes and provide a segue to Jeremy's work with Jeremy, basically. So just kind of briefly outlining kind of the last direction from my part, mainly an outlook in how we can use data, or how we can adapt to data that is not only from a different distribution, but also from a different task. And here mainly going to focus on how we can use pre-trained language models to do that. And essentially, the setting here, similarly to before, we have one source domain, but in this case, the source domain or the source task is essentially going to be language modeling, and in particular for our case, where we train on the Wikipedia dataset, and we're going to try to adapt to an arbitrary target task, essentially, and focusing here in particular on different text classification datasets. And just briefly here, I'm sure most of you are aware of this. So the status quo, as we've seen it for like transfer learning for NLP, is that in many cases, really just using pre-trained word embeddings is really the best practice. And there's been a lot of recent developments that try to use more of transfer learning, that use that use embeddings from pre-trained on different tasks, like machine translation or language modeling, like in Elmo, as fixed features. And but in Elmo, for instance, you still require kind of a state-of-the-art architecture around that, and still require to train that architecture using your fixed language model embeddings as features. Whereas in our case, we really try to come up with a method that could be applied as is to every task, basically. And our main intuition here was that instead of just initializing the initial layer of our models with the pre-trained embeddings, why don't we have something, or why don't we find a good initialization for our entire neural network? And the main direction we're taking here is not new. So the first idea in this direction had been proposed in 2015 of fine-tuning a language model. And in contrast to that work, we add kind of this step that we found very crucial, is that we pre-train our language model on a general domain corpus, as had been done in Elmo as well. And in addition, we propose different techniques to minimize the risk of catastrophic forgetting during fine-tuning, so to retain as much information as possible during that we acquire during that language model pre-training step. And so just briefly here, the kind of main 3 steps of our method is that we first train language model on general domain corpus, like Wikipedia. Then we fine-tune our language model on the data of our target task, like IMDb. And then finally, we train a classification layer on top of this language model. And so just briefly, for training the language model here, we use a state-of-the-art LSTM language model that is really just a vanilla LSTM consisting of 3 layers, and doesn't really have any fancy tricks or other sophistications, and only uses tuned dropout hyperparameters. And we train this model on kind of a general domain data set, and we chose the Wikitext 103 dataset, which consists of about 103 million tokens of Wikipedia, and we trained that model for about 24 hours on one GPU. And in our case, we actually tried also training that on, for instance, on order of magnitude more data, but we didn't observe too much improvement from doing that when keeping the architecture fixed. Although we would kind of assume, or the intuition maybe is that if you make your model deeper or make your model more expressive, by, for instance, adding skip connections, you could potentially get more benefit out of training that on a larger amount of data. And kind of this, intuition maybe has been kind of validated recently from work at OpenAI, where they essentially did kind of a similar approach, but training a deeper model on more data for a much longer amount of time, and also observed improvements on different downstream tasks. And then briefly here for fine-tuning, I'm just going to briefly touch on that, so Jeremy has still enough time to talk about his part. So we essentially proposed different methods to minimize the risk of losing the information we have retained before, and mainly because from computer vision we know that the information or the information that is captured in the lowest layer of our model is the most general, and as we go higher, the information gets more task specific. So we train our model with different learning rates for different layers, mainly using lower learning rates for the lower layers and higher learning rates for the higher layers. So we only update the lower layers to a lesser extent, basically. And then secondly, we also found it useful to essentially use kind of a special learning rate schedule that increases the learning rate rapidly and then slowly decays that over the course of training. And then finally, for fine-tuning the classifier, we found it very useful for the model to make it easier for the model to backpropagate the information, in addition to just using the final hidden state for prediction, to also use a max pooled and a min pooled representation over the hidden states to just make it easier for the model to use information in the final classification layer. And in addition, we also found it useful for the final classification to make it easier for the classification parameters to adapt to the remaining parameters of the model, to first only train the classification layer in the first epoch, and then from then on essentially gradually unfreeze the remaining parameters, so train the top two layers in the second epoch, and keeping the remaining parameters frozen, and gradually unfreezing the remaining parameters layer-wise during training. And then secondly, even though a language model is inherently unidirectional, we can obviously also train a backward language model, and just for simplicity in our case, we train them independently and then just ensemble predictions in the end. And briefly, we train our model here to really show that this kind of approach is general and can be applied to a diversity of different tasks and domains. We evaluate on 6 different different text classification tasks, ranging from question classification to sentiment analysis to topic classification, with a diversity of different number of classes, a number of training examples. Exactly. And we compare that against state of the art. I'm not sure. Do you want to walk? Okay, awesome, cool. So thanks for listening to me, and now you have the pleasure of listening to Jeremy.
I just, where are we? This way around. Thanks. Wow, this is a bit stiff, huh? Yeah, got it. Yeah.
Perfect. Cool. And you have here the clicker.
Oh, thanks. I just wanted to give some context around this because it's kind of interesting as to where this all comes from. Basically, I'm a researcher at FastAI, which is a research lab. Also create, it's kind of similar to AI2. We also create software. In our case, we also teach a course. And we had been doing quite a bit of stuff with computer vision and been getting some good results in computer vision. And I actually wanted to prepare a lesson for our online course showing, we kind of feel like transfer learning is the most important thing in practical day-to-day deep learning for regular applications. It kind of lets people use a lot less data. And so I wanted to show people, okay, here's how you do transfer learning in other areas, not just computer vision. And I'm not an NLP guy, so I looked around the internet and I found a really great blog post by this guy called Sebastian Ruder, who would basically put together all this information on transfer learning and multitask learning. And I looked through it all and I was like, wow, this is a great blog post, but all these approaches look terrible. Like they didn't give good results. I was really surprised. And so, I kind of thought like, well, why aren't people doing all the stuff that we're already doing in computer vision in NLP? So that was the starting point. It was like, well, let's try that. And so this bunch of stuff that you see here, a simple model that's pre-trained, followed by discriminative fine-tuning, slanted triangular learning rates, concat pooling, gradual unfreezing. This is all the stuff that we teach literally in lesson 1 of our course for computer vision. So we just thought, let's do that for NLP. And so that was kind of the starting point of this paper, was steal all these approaches from computer vision, which we spent quite a bit of time finding these best practices and building some of them and kind of, see what happens. And so the particular focus was IMDb. IMDb is a classic classification problem where you're trying to find the positive sentiment movie reviews and the negative sentiment movie reviews. And I find it a really interesting data set because it's about 1,500 to 2,000 word long documents, which is very similar to the length documents you get in an industrial setting a lot of the time, like radiology reports or emails or stuff like that. So it's like a really good data set to use if you want to see how well things are going to work kind of for standard day stuff. Much to my surprise, the first time I tried transfer learning from a language model to IMDb, I immediately had a better result than I could find in the literature on IMDb. And I found this surprising because, like I said, I'm not an NLP guy. It was the first thing I'd ever tried for NLP. So I kind of thought, wow, this is really encouraging, this idea of taking stuff from computer vision and stealing it and seeing what happens. So I actually did this lesson, and I taught it through our course, and then Sebastian was kind enough to watch the video, and he got in touch with me and said, like, this is interesting enough, it should be not just in a video, it should be in a paper as well. And I was like, I don't want to write a paper, that sounds boring. And Sebastian was like, oh, I'll write the paper. So he did all these experiments and he wrote the paper, and he found lots of other examples of interesting classification data sets, and we found in every case we got a state-of-the-art result, and we didn't really have time to do a lot of fine-tuning with these, so like these were done pretty quickly, basically. So I think we can probably take these further. There's nothing particularly about classification, as Sebastian was saying, that for this technique it will work equally well, we think, on sequence labeling and sequence to sequence. It's just, the first thing we happen to try. And also, it's one of these things that I feel like it's really underappreciated in the NLP academic context, is how important classification is. In industry, in medicine, and stuff like that, there's a lot of things turn out to be classification tasks, like legal discovery is a classification task, spam prevention is a classification task. A lot of stuff in medical triage is basically a classification task, and so forth. So it's also something like really valuable thing as a starting point to work on. One of the really interesting things here was that we found that when you looked at, so Sebastian ran these experiments where he tried smaller subsets of the IMDb data set, right? And we found that when we did the semi-supervised approach, we were getting classification results that were close to the state-of-the-art with just 100 labeled points, right? And so again, this is something that we think is really important in practice, because you really want something where you can say to somebody like, hey, go and classify 100 of your documents and then run this, and you'll get pretty good results.
So can you clarify what the supervised and semi-supervised variants are?
So one is the IMDb data set comes with a unsupervised folder.
Yeah.
So the approach is, first of all, pre-train on Wikipedia.
Yeah.
And the nice thing is we then make that model publicly available. So you don't have to run the 24 hours. which we've got down to 3 hours now, by the way. We can do that in 3 hours. And then fine-tune the language model on an in-domain corpus, which is going to be your documents. But the IMDb dataset also comes with a folder of unlabeled documents. So that's the semi-supervised bit. So it's basically
So
how much data did you pre-train?
You're using more data, more unlabeled
More
data,
unlabeled
and
data.
in-domain for the yellow line.
Exactly.
Yeah.
Yeah. Okay. So this is to me the really interesting thing because, as I say, I've spent more time in computer vision, and we've definitely found that when I talk to people in scientific and medical and so forth communities, the thing that really matters to them is how much can I do with smaller data sets. Like in radiology, it takes about 15 minutes to properly mark up a CT scan, and you're paying radiologist level prices. You really want to reduce that time and cost. One of the interesting questions here is why a language model? And actually, my background originally was in philosophy, and it was interesting to me because this guy called Searle wrote a really important thought experiment years ago called the Chinese room experiment, where he was trying to answer the question, is it possible to learn semantics from syntax? And his claim was no, right? And so there's been this long philosophy battleground around, can you learn semantics from syntax? And this very idea of starting with a language model is basically saying Searle was wrong, right? We're basically starting with nothing but syntax and are trying to learn something useful. And so when you think about it, to create a really good language model, you need to be able to kind of finish a sentence like, I ate a hot, what, dog? It was a really hot, what, day, right? You can't finish those with n-grams, right? You finish those by understanding something about the world, right? And so it's interesting to note that if you want to create a really good language model, it actually needs to get some kind of word knowledge. It actually world knowledge. It actually needs to learn some kind of semantics. So it's kind of for me as a long gone philosopher, it's interesting that we're basically kind of using this cognitive science philosophy of mind question and kind of trying to answer it here and saying like, oh, it actually turns out we are learning enough in a language model that we can, with just 100 documents, turn it into a sentiment model, right? So if you want to create a really good language model, it needs to understand things like what do people sound like when they're happy versus when they're sad, or what do people sound like when they're saying this is a malignant tumor versus a non-malignant tumor or whatever. So the language model, turned out to be really kind of interesting, and then it's particularly useful pragmatically because you have this idea that Jan LeCun calls self-supervised learning. So a self-supervised model is one where it's a supervised model, but the information about what you're learning is in the original data set. So a language model is self-supervised because you don't need separate labels. The label is just what's the next word. So if generally speaking, if you can come up with a way of doing pre-training using a self-supervised model, it's kind of like the magic trick, right? So there's a similar idea in computer vision, which is you train something with a few frames of a video, and you try to predict the next few frames. And so that's the language model of computer vision. And indeed, it turns out that in computer vision, that self-supervised model is absolutely fantastic at building something that you can use in lots of different places. One of the things I've heard a lot from people, so for example, talking to the guys, Alec Radford and the guys at OpenAI that did the follow-up paper that Sebastian mentioned, they said that the main thing they got out of our ULM-FIT paper is this idea that you actually don't need really to train that much on in-domain data. Just training on Wikipedia is totally good enough, right? And a lot of people find that counterintuitive, right? So the guys at OpenAI were doing all this work on trying to get more in-domain data, and then they saw our paper and they were like, oh, it turns out you don't really need it. And so the intuition for why this is, why does a language model just on Wikipedia work so well, even though Wikipedia doesn't have movie reviews, it doesn't have people saying how much they liked Kevin Costner in this movie or whatever, why does it work well to create something that gives us movie sentiment? And the answer is, when you start with an untrained neural net, you have random weights, right? And random weights don't understand anything about English. I'm using understand in a very fuzzy way. Don't yell at me about it, okay? It doesn't understand anything about English. Once you've got something that can predict the next word of a Wikipedia article pretty well, and when I say pretty well, we're talking like 35 to 40% accuracy. So they really are pretty good, right? Then by that point, it needs to know quite a lot about grammar and kind of context and sentiment and all these other things. So you kind of, from random weights up to know enough about English to predict the next word in a Wikipedia article is a huge step compared to knowing enough about English to do that to knowing enough about English to predict whether a movie review is positive or negative is a relatively small step, all right? So a lot of people, when they ask about our work, have asked me, well, how do I go about replacing the Wikitext pre-trained model with something that's trained on 1 million radiology reports or something? And what our result really found here is you don't have to. It really doesn't help much, if at all. Just a pre-trained Wikipedia model is plenty good enough. A couple of interesting results to add, which weren't in Alec Radford's paper. That OpenAI paper, even though it trained a bigger model on more data, got less good results on IMDb than this, right? So actually, there is some suggestion that maybe even if our model was bigger and trained on more data, maybe it doesn't help. Like it does seem like this 103 million token language model is, a pretty good point, basically. So, next steps for this, I guess, do you have a browser here I can run, Sebastian? Is this your, what do I do? Can you bring up nlp.fast.ai? I just wanted to show them that one. I guess what happened in computer vision after ImageNet pre-trained models started popping up is it really changed the field quite a lot. For you guys that were involved in that, you'll remember suddenly far more people could use computer vision for their day-to-day tasks. And we have a lot of our students literally creating very effective classification models with only 15 or 20 images per class now by fine-tuning ImageNet models. So what we're doing is we're trying to kind of provide the same infrastructure now for fine-tuned language models. So we're setting up a model zoo so that people can, we've got basically trying to create pre-trained language models in every language that has a Wikipedia. Trying to do the same thing for sequence-to-sequence and sequence labeling, which I'm pretty sure should work pretty much just as well. And also show examples of this approach on non-English classification data sets. And then Sebastian's been working on taking some of the stuff from the FastAI library and putting it into NLP so we can both use it in that library and compare more easily. Like one key question at the moment that we don't know the answer to is how important is a fine-tuning step? So as Sebastian mentioned, Matt's paper, the Elmo paper, doesn't fine-tune the language features but can take advantage of task-specific models. Our approach fine-tunes the whole lot, but has a kind of a single standard 3-layer LSTM as the model. So we want to compare these approaches better. In the computer vision world, the fine-tuning approaches turn out to work better than the non-fine-tuned. The non-fine-tuned approaches in computer vision are called hypercolumn-based approaches. So, we're hoping to be able to compare these things more directly. And then we're also trying to bring more of these ideas back into the FastAI library so that people can, use them more easily. Is that a fair summary? Anything else you wanted to add?
No.
Yeah. Anybody have any questions about this paper or the overall direction?
Yeah. So with the single model architectures and the fine-tuning approach as opposed to the Elmo approach, are you able to solve sort of like word level tasks? Because I know a lot of what I've seen have been sort of like level classification tasks, but then if you want to do something like
Yeah, so things like sequence labeling, like I say, we haven't done it yet, but I'm 99.9% sure it'll work fine, and we hope to show it soonish. Like basically, if you've, a language model is something that knows how to predict the next word of something. Just like with the classification, you can strip off the decoder and stick on some new custom head. So in this case, your new custom head would just be something that does, word by word predictions, part of speech tagging or whatever. Yeah. Like in general, like I say, I'm not really an NLP person, so I'm much less familiar with this. I've done a little bit of sequence to sequence and sequence labeling and stuff, but in computer vision, like the whole FastAI library is set up to make this trivially easy, that you've got any kind of pre-trained model, and the system already knows how to pop off the equivalent of the decoder and pop on a task-specific custom head, and then just fine-tune that automatically. So the goal is to have exactly the same thing for every NLP task that people do.
I think with that, we're about out of time. Sebastian, Jeremy will be around today. I know a lot of you have one-on-one meetings scheduled with them. Otherwise, let's move around.